Okay, all right. So I work for a company called Digital Silence. We're a Denver, Colorado-based security consulting firm. Um, I'm basically a senior security assessment manager and co-founder there. Used to work for a company called Gotham Digital Science. They have an office in London, so you might have heard of them. Also used to work for a defense contractor called OG Systems. Probably haven't heard of them. Basically a little bit about me. I'm a red teamer, researcher. New dad, which is pretty cool. I have a pretty interesting LinkedIn handle. It's ms08067. But yeah, enough of that. So this is a talk about, mainly about attacking 802.1x 2010. But before we go into that, we should probably go over just kind of like how 802.1x itself works. So what is 802.1x? It's an authentication protocol. Welcome, everyone. And it's used to protect local area networks and also wireless local area networks with rudimentary authentication. It defines an exchange between three parties. The supplicant, which is the client device that you're connecting to the network, the authenticator, which is a network device such as a switch that's providing access to the network, and you also have the authentication server, which is a host that's running AAA software such as Radius that is going to make authentication decisions, what can and cannot be able to access the network. And that's usually sitting deeper inside the network, but communicates with the authenticator. You can think of the authenticator, which is once again is your switch, as a sort of gatekeeper or security guard. The supplicant's going to connect to it and provide it with credentials and as well as its identity. The authenticator is going to forward these credentials to the authentication server. But the authenticator itself actually doesn't have any decision-making power. That's actually, that's a role that's assigned to the authentication server. Once the authentication server receives these credentials, it's going to validate them and then make a final decision as to whether or not this device can access the network, and the authenticator is then going to carry out that decision. 802.1x is typically a four-step sequence. So it's going to start out with initialization, then initiation, negotiation, which is basically EAP negotiation, and finally move on to authentication. Ports have two states. So if you have a port that's protected by 802.1x, it can either be authorized, in which traffic is unrestricted. You can send anything you want through that port, or unauthorized. So it's unauthorized, which is the default state. Traffic is restricted to only 802.1x traffic. So we mentioned the first step of this process is initialization. Initialization, basically what's happening is that the supplicant's going to connect to the switch port, which is going to start out as disabled. The authenticator is going to detect this new connection, enable the switch port in the unauthorized state. And then we're going to move on to initiation. And basically what initiation means, it means you're initiating the authentication process. Either the supplicant or the authenticator can start this. If the supplicant's starting it, it's going to start by sending an equal start frame. The authenticator is going to respond with an EAP request identity frame, which is basically asking the supplicant, who are you? So it's going to basically asking for its username. The supplicant's going to send a response identity frame, which is going to contain an identifier such as a username, and then that's going to be received by the authenticator, which is going to encapsulate it into something that the Radius server or the authentication server can understand, and it's going to forward it to the authentication server. At that point, we transition to step 3, EAP negotiation. So long story short, 802.1x is basically an encapsulation of EAP, Extensible Authentication Protocol, for use on wired networks, and also, as we said, in some cases on wireless networks. So there are many ways of implementing EAP, and we're going to talk a little bit about that later. But basically, at this stage, what's going to happen is that the supplicant and the authentication server are going to haggle for a bit until they decide on basically both agree upon an EAP method that they're both comfortable with. Once that happens, you move on to step 4, which is authentication. And we mentioned that EAP is kind of like, you can implement it a number of different ways. So the specific details about how step 4 is going to play out are dependent on the EAP method that we chose in the last step. However, the important things to remember here is that this process is always going to result in either an EAP success or EAP failure message. As you may guess, EAP success means that the authentication attempt succeeded. If we have an EAP failure, it means that it failed. So what's going to happen if we get the EAP success message is the port's going to be set to authorized, and all traffic can flow through freely. So we've been talking a lot about EAP, so we should probably go over what that's all about too. EAP stands for Extensible Authentication Protocol. It's really more of an authentication framework. It's not really a protocol because it only defines message formats. And individual EAP implementations are known as EAP methods. So you can kind of think of it as a black box for performing authentication. You know that if you give it a specific set of inputs, you're going to get a specific set of outputs, which either you're going to get an authentication success or an authentication failure, plus some other stuff. But the actual details are really just kind of boiled down to the specific implementation. Some notable implementations or methods. EAP MD5, big spoiler alert, it's really bad. EAP PEEP, it's another spoiler alert, it's not quite as bad, but it's still pretty bad. I know it's just soap, but it looks delicious, so I just had to throw it in here. EIP TLS. So traditionally, EIP TLS is one of these EIP methods that has been thought to be a lot better than the other ones we just mentioned. And actually, that's true. It's probably one of the more secure ones. There was some research released at DEF CON last year by a couple guys from SensePost, or last month, should I say, where they kind of nuked that assumption to some degree. So yeah, that kind of paradigm's changing a little bit. But anyways, that's the AP. I guess the next thing we got to do before we kind of get to the meat of what we're talking about today, is talk about just go over like a brief history of wired port security and essentially why we're doing this research in the first place. So the 802.1x standard came about in 2001, and the first version of it was called 802.1x 2001, and it was created to provide authentication for local area networks. Fast forward 3 years to 2004, and we have 802.1x 2004, which added a whole bunch of new stuff with the primary intention of extending 802.1x so you could use it over wireless environments as well. A year after that, in 2005, there's a researcher named Steve Riley who demonstrated you could actually bypass 802.1x 2004 by inserting a hub directly between the supplicant and the switch. So essentially, like you have the switch and the workstation, whatever's connecting to it, you put a hub on it and you can sniff traffic, which is pretty cool because it's a passive bypass. You could also interact with the network in a limited degree. You can inject UDP packets, although with Riley's implementation, if you do a TCP injection, it causes a race condition and things start to break. So you couldn't really do that. That was fixed in 2006, though, which, basically like 6 years later, and that was, so essentially two things happened in 2006, I'm gonna say 2011. Two really interesting things happened in 2011. The first thing that happened was Ab from Gabriel Security created a tool called Marvin, implemented in Java. The major breakthrough with Marvin was the fact that you no longer had to rely on a hub to bypass 802.1x. Instead, you could place a rogue device directly between the supplicant and the switch. So you'd have two network interfaces, and you'd plug one into the switch and one into the workstation, the supplicant device, and you just bridge traffic. You use a Linux bridge to kind of forward traffic between these two interfaces, and that would allow you to passively, just kind of sit there on the network and inspect traffic. And additionally, you could, with ABS implementation, you could get full interaction with the network using packet injection. Later that year, this is like one of those cases where two researchers kind of came up with like something very similar, and we're working in parallel and didn't even know it. Alva Duckwall released something, his own 802.1x 2004 bypass, that also used a transparent bridge, to kind of introduce the rogue device between the supplicant and switch. But the cool thing about Duckwall's implementation is it didn't actually need packet injection because he just used IP tables to create a source NAT so that all traffic originating from the rogue device would appear to be coming from the supplicant. So that was a much simpler implementation. It was all done in Bash, and comparatively, it had a lot less that you could. There's a lot less setup. So that's kind of like when people think of how to bypass 802.1x 2004, this is usually what they think of. And we're going to go over that a little more later. 2017 in Hack in Paris, so actually very recently, Valerian Legrand created a tool called Fenrir, which works similarly to Duckwall's tool, but implements the natting in Python using Scapy. Because by this point, Duckwall's tool is pretty old, wasn't maintained at the moment, and relied on kernel patches that no longer existed. So Legrand kind of fixed that, threw it into a module design with support for responder and all kinds of other stuff. So I think whenever you're starting a new research project, it's not only useful to kind of try to understand the existing work out there, but also to see if you can implement it yourself and even improve upon it if there are ways that you can. So with that in mind, let's look at Duckwall's classic 802.1x bypass a little more closely. We mentioned it used a transparent bridge to silently introduce the rogue device between the supplicant authenticator, and network interactions achieved using IP tables to create a source NAT, so the traffic originating from the rogue device appears to be coming from the supplicant. Interesting problem that Duckwall had to face is, when you think about the situation you're going to be in if you're trying to bypass 802.1x, in most cases, you're going to be in an environment where you're not supposed to be there. This is the kind of thing you have to do on a red team assessment when you've broken into a building and you actually need to like plant something. So presumably you're not going to have a lot of time to stick around and fiddle with this stuff. You need something that you can plug in, leave behind, and then later have a way of connecting back to this device, getting access to it, and doing everything else you need. So it's important to have a way of accessing this device from, essentially remotely. So Duckwall's answer to this, and we'll go into like a little why. We'll go into why you have to do this a little bit later. But Duckwall's answer to this, he did two things. The first thing he did was he uses destination natting to create a hidden SSH service. that essentially you could access from a very specific IP address with a very specific route setup, et cetera, if you were on the internal network. But also because you can't guarantee the ability to connect to a device that's behind like an NAT and firewall and all this other stuff. You also implemented it so that you could set it up so that you have an outgoing SSH tunnel that would allow you to essentially, it would give you a reverse shell essentially that you could connect back to the device. He did this over port 22, but you could do it over anything really. The other problem that Duckwall had to face, which was kind of interesting to me, is that when Duckwall created his original tool, the Linux kernel at the time would not forward ePOL packets over a bridge, and presumably for security reasons. And that's kind of what we're doing to do this bypass in the first place. So what he did, and what pretty much all existing tools do to solve this problem, is to patch the Linux kernel, so that essentially you change some stuff, and suddenly the Linux kernel will forward packets over the bridge. So existing tools either do it that way, or they rely on high-level libraries such as Scapy. We mentioned Legrand's tool that does that. There are some problems with these approaches. Basically, relying on kernel patches can become unwieldy. Actually, and the fact that there are no publicly available kernel patches anymore that do this is testament to that. You figure what it's like to try to maintain a patch that modifies something from what the kernel's supposed to be doing. You need to keep updating that patch as the Linux kernel continues to be updated over time. And people move on from these tools. So essentially, if your tool, like, if you're relying on a kernel patch and development of the kernel suddenly starts to go this way, and something that existed in one file now is in two or is in somewhere else, the patch is going to break, and your tool is no longer going to work. And the problem with relying on higher level tools such as Scapy is that it can actually make the bridge kind of slow under heavy loads. You won't notice it at first, but it will, in circumstances where you have a high volume of traffic, create a bottleneck. And a bottleneck's a really good way to get caught. Because not only do you have the security guys who knows the spike, but now you have like users complaining that their network is slow, and then here come the network admins looking for the bottleneck, and they find a little sketchy box that plugged into the network. That's a problem. So fortunately, the situation's actually dramatically improved since Duckwall originally made his tool that did this. As of 2012, ePOL bridging is actually, you can actually enable it in the Linux kernel. It's not on by default, but you can interact with something called the pros file system, which you can kind of think of it as like an API for the Linux kernel for changing configs on the fly. It's basically a bunch of files, and you modify the values in the files to do that. But you can actually enable it using the pros file system. And what this means is that you don't have to rely on patching anymore. So I added that to my implementation of this, and just use the pros file system, so you don't have to do patch the kernel anymore. The other thing that I added was support for side channel interaction. We mentioned that when Duckwall created his original bypass, he had to figure out how to provide the attacker with access to the rogue device from a remote location. This was back in 2011. Cellular modems were pretty unsophisticated. They were slow. They were really expensive. You couldn't just go down to whatever your local electronics store and buy like a USB LTE modem, or that wasn't like really something that was available on the commodity market. So the solution, his solution was to create the hidden SSH service and rely on SSH. There are drawbacks to this approach, though, which now that a few years later we can actually mitigate. The first problem is that it relies on the assumption that egress filtering is something that can be bypassed, which it's not always going to be something you can rely on if you have the outgoing connection. The other issue is that relying on pushing traffic through the target network is going to create another opportunity for detection. So the updated implementation of this, what I did essentially was I modified some of the firewall rules in the original scripts to get it to work. So now you can add a side channel interface, whether a modem, some kind of like RF device or whatever. It doesn't really matter. But you can actually control the whole thing through a side channel interface and not have to rely on going through the target network to maintain control over your device. So I'm just going to demo this really fast. And I know you can't see it on my end, but my screen is really, really small for some reason. So if I mess this up, please forgive me. OK, so what you're going to see here, can you guys see my mouse? OK, cool. Wow, the mouse looks totally different over there. OK, so in the bottom right, we have the authenticator, the switch. Top right, we have the supplicant. On the left, we have the attacker. If you see this little Ethernet cable, the yellow one all the way on the right, that is connected to the supplicant. And that little green light, or it should be green anyways, it'll be green in a second. I can't actually see it. That little green light right there indicates that something is currently both connected to that port, and it's currently authenticated. What you see here is this device is pinging out to the outer network. It's something outside the network, specifically Google's DNS server. And the reason why we're doing that is just to show that this thing has connectivity. When we connect the rogue device, you're going to notice that this stops because it's going to lose connectivity briefly. By the way, if this light turns off, like you just see, that little green light, if it turns yellow, it means authentication is currently in progress. If it turns off and stays off, it means that either nothing is connected to the port, or it thinks that nothing is connected to the port, or authentication has failed and we've tripped port security and that's been completely disabled. So, all right, let me actually try to run through this. Whoa. I feel like I'm playing helicopter, you know, that little arcade game? Yeah, okay, there we go. So we're gonna run this command and it's gonna create our bridge. And you see that we've lost connectivity here from the supplicant's perspective. But now that we've created our bridge, you can actually, this turned yellow because the supplicant's re-authenticating through our rogue device. And now, you know, we've re-authenticated in the light screen again. So that's the, that gives us our passive bypass. If you want the active bypass, you have to add the source netting. So you just run a second command. All those little flags that have data in them, you can actually sniff that when you're in the passive bypass mode. So we're gonna run the active bypass by creating the source net. And I'm gonna just kind of fast forward this a little bit to save time. But once it's done doing that, you can actually interact fully with the network. So just to demonstrate that that works, it's going to do a port scan, bless you, of hosting the internal network. You see it worked, so that's that. All right, so all these traditional 802.1x bypasses, you know, the hub-based one, the injection-based one, the bridge-based bypasses, they all take advantage of the same fundamental security issues that affect 802.1x 2004. And that is that the protocol does not provide encryption, and the protocol does not support authentication on a packet-by-packet basis. Which is kind of why 802.1x 2010 was developed. It's the latest revision of the protocol, and it uses MacSEC to provide layer 2 encryption on a hop-by-hop basis and packet-by-packet integrity checks. So this is pretty cool because not only does the hop-by-hop encryption help you protect against the bridge-based attacks, but it also allows network administrators with means to inspect data in transit. Because remember, the encryption is going hop by hop, so if you know, in between hops, you can still look at traffic. The 802.1x 2000 protocol works in 3 stages. Begin with authentication and master key distribution, then we have the session key agreement, then we move on to the session secure stage. So the authentication stage is basically just, in all intents and purposes, it's pretty much 802.1x as we described previously. You know, you have your initiation, your initialization, your negotiation, you pick an AP method that works with whatever you're doing, and then you perform authentication. And if it's successful, you move on to stage 2, where you have the session key agreement, which actually isn't horribly relevant to the bypass, believe it or not, but that we're going to do later. But yeah, essentially during the session key agreement, the important things that happen here is that the session keys get installed. Well, first you establish the supplicant can actually support MacSEC in the first place, and then you install the relevant session keys on it. And then if all that succeeds, you move on to stage 3, which is session secure. And at this point, everything's protected by MacSEC, or should I say like the layer 2 encryption provided by MacSEC. And this is ultimately where you're trying to end up. So I think whenever you're trying to approach like a challenge in terms of finding a way to attack a new technology of some kind, it's useful to look for parallels between this this new technology and also things that have been either exploited or bypassed or compromised in the past. So with that in mind, this particular clause in the IEEE standard for 802.1x 2010 actually kind of stuck out at me. It's in section 6.6, and basically what this clause is alluding to is that there are parallels between the role that MacSEC is playing and the roles that similar encryption kind of things are playing within 802.11, which is what you use to implement wireless communication. And what kind of stuck out at me is they must probably be talking about WPA. And indeed, there are parallels between MacSEC and WPA, although perhaps not the ones that they were intending to allude to. But when you think about WPA, it came out in 2003. That's when you had WPA 1. It also provided hop-by-hop layer 2 encryption from the access point to the base station being your whatever device you connected to the wireless network. It was also providing authentication using so WPA provides an authentication using either EAP or pre-shared key as a fallback or alternative. There's a major kind of paradigm shift that happened in the offensive security community when WPA was released, excluding the whole slew of TKIP-based attacks, which kind of ended up getting mitigated by WPA 2, at least for a pretty long time. injection-based attacks were no longer possible due to the layer 2 encryption, the strong layer 2 encryption being provided by WPA. So this kind of led to a focus shift because you couldn't do the same style of injection-based attacks that worked against WEP. So you kind of had to do a focus shift and focus on attacking the authentication mechanism. And in fact, if you look at the traditional ways that you would breach a WPA network, the first, if it's a PSK network, you have the WPA handshake capture and subsequent dictionary attack, and that's attacking the authentication mechanism. You also have the rogue AP attacks against weak EAP methods. So fast forward a bit to 2010, and 802.1x 2010 is released. It's providing hop-by-hop layer 2 encryption using MacSEC. This time between either device to the switch or from two switches, from one switch to another. But it also is providing authentication using EAP or PSK as a fallback or alternative, which you can kind of see where I'm going with this. With this, bridge and injection-based attacks that used to work against earlier versions of 802.1x no longer work. So I guess the first thing that kind of comes to mind is to try attacking the authentication mechanism. And this is pure conjecture, but I would assume that some dictionary attack, it would be at least worth exploring some kind of dictionary attack against the PSK variation. I haven't really fully delved into doing that yet, so I can't really tell you one way or the other. But the other one that's kind of obvious is to try attacks against weak EAP implementations, which is the main takeaway of what we're going to talk about. To kind of understand what we mean by attacks against weak EAP implementations, we're just going to go over some attacks that work within a wireless environment when EAP is used, or weak forms of EAP are used. You see this diagram here. This is a diagram of the EAP PEEP authentication process. EAP PEEP is an EAP method. It's very, very closely related, very similar to EAP TTLS, which EAP TTLS makes a little more sense within an 802.1x 2010 environment. But they're close enough together that you understand one, you can understand the other. But the way EAP PEEP works is that first the supplicant, which you see on the left, which in this case is a wireless device, is going to make an authentication request. It's going to make an authentication request to the authentication server. Now, the authentication server is going to respond with an X509 certificate. And the role of this X509 certificate is to prove to the supplicant that it is who it says it is. Before this happens, the supplicant really has no idea what it's connecting to. So the authentication server has to prove that it can be trusted. Now, the supplicant at this point can choose to either accept or reject the certificate. If it accepts the certificate, it means that it trusts the authentication server, it trusts who it says it is, and it feels safe to authenticate to it. If it rejects it, this whole thing is called off and nothing further happens. So provided the certificate's accepted, and the onus is kind of placed on the supplicant and in a lot of cases the user to accept or deny this. But if it's accepted, you're going to move from the outer authentication to the inner authentication, which is the next stage of what we're showing here, in which a secure tunnel is established between the supplicant and the authentication server. And then what happens through that secure tunnel, or what happens is that the actual, the meat of the authentication process, where you actually type in your password and that gets, converted into a hash that gets sent to the authentication server, that happens through that secure tunnel that we've established. And the reason for that is because, and we'll talk about this more toward the end of it, with earlier versions or earlier EAP methods that didn't use a secure tunnel like that, you can actually sniff this whole process offline. So there are some issues with this process. Brad Antonowicz and Josh Wright back in 2008, they actually demonstrated that you could use a rogue access point attack to force the supplicant to authenticate with the rogue authentication server. By rogue access point attack, what we mean is there's a style of attack, different variations of the rogue AP attack, but I guess the most fundamental form that's kind of easiest to understand is the evil twin attack, in which essentially you create a clone of the target access point with the same network name, and so long as you can provide a better connection to these client devices here, they'll connect to you. And there are a couple ways of doing that, either higher signal strength or better signal, or simply by spamming this one with deauthentication packets. Once you do that, you've essentially established a man in the middle. And remember that until this whole process succeeds, this essentially is operating as an open network because you need to authenticate before the WPA protections kick in. So what they figured out was that you force these devices to connect to you, and then you run your own authentication server in the background, and they authenticate with you, and you can capture, in this case, an MS-CHAPTER-2 challenge and response, which are hashes that you can crack to obtain credentials. Did that make sense to everyone? Because that's pretty fundamental, so I just want to make sure. Are we good with that? Anyone not good with that? Okay, awesome. Right. So to make this worse, right? Like what they also, the thing is, like EAP PEEP also uses, well, okay, so we mentioned that EAP can be implemented in any number of ways, right? I mean, there's a ton of EAP methods out there. Likewise, when we talk about the inner authentication that happens through this secure tunnel over here, there are a number of ways you can implement that. MS-ChaPy2 is probably the most widely used for EAP-PEEP and EAP-TTLS. Also one of the stronger ones. I mean, what's cool about MS-ChaPy2 is it actually does provide mutual authentication, which is pretty interesting. The problem is it's also vulnerable to a cryptographic weakness, as discovered back in 2012 by Moxie, Marlon Spike, and David Holton. And essentially what they figured out is that the MS-ChaPy2 challenge and response is what you capture in order to crack and obtain passwords. The MS-ChaPy2 challenge and response can be kind of converted to NTLM-v1, which, as you may know, can itself be reduced to a single 56 bits of DAS encryption, which can be cracked really fast. This was back, like 6 years ago. They were able to demonstrate that you could crack essentially passwords of arbitrary length within 24 hours with 100% success rate using an FPGA-based cracking rig that they built. Now, granted, their rig that they built was a $100,000 FPGA-based cracking rig. So it was kind of expensive. However, they did make it public, so they, to kind of nuke the argument that, well, most people couldn't have access to this. So they essentially said, well, you can use ours. Actually, I had the pleasure of speaking with Mr. Holton last summer, and he was telling me that that $100,000 cracking rig that cracking rig they built back in 2012 that cost them about $100,000 to build, now would probably cost anywhere between $10,000 and $20,000 to build. So that actually is a number that's much more approachable in terms of what would be affordable to a mid-grade, like criminal enterprise, or at least something you could find someone to crack these hashes for you. So it's actually far more within reach of that because the hardware to do this has gotten cheaper. But anyways, back to 82.1x 2010. And why are we talking about this stuff in the first place? Okay, so the main takeaway about 82.1x 2010 from an attacker's perspective is that it uses EAP to authenticate devices to the network. And that's all well and good, but it's important to remember that EAP is only as secure as the EAP method used. And if we look at the EAP methods that are supported by 82.1x 2010, basically the only requirements are that it supports mutual authentication, that it supports derivation of keys that are at least 128 bits in length, and it's able to generate an MSK of at least 64 octets. And there are plenty of commonly seen weak EAP methods that meet these requirements, including EAP-PEEP, EAP-TTLS. So I think you see where I'm going with this. So it makes sense now that we should be able to use a similar attack to what we use to defeat weak EAP methods on the wireless environment within a wired environment. And I know the slide says defeating MacSEC using rogue gateway attacks. We're actually not doing that. It should say defeating 82.1x 2010 using rogue gateway attacks because what we're about to do, we're not actually going to approach MacSEC at all. We're going to avoid having to deal with MacSEC by attacking authentication mechanism, which it's kind of sleazy, but it works. So the goal of a rogue gateway attack is to force the supplicant to authenticate with the attacker's device, and this is happening on a wired network. Once this happens, you capture hashes, crack them, and authenticate directly with the network. The challenge here is going to be that we're no longer working with wireless. We can't just pluck devices out of the sky and get them to connect to us. We have to be a little more clever in terms of, or not, as the case may be, in terms of actually getting this to happen. But you can't use the traditional rogue AP attack that would work in a wireless environment. With that said, if we look at 82.1x 2004, the bypasses that affect that, they take kind of a man-in-the-middle style approach. You see we're inserting the device directly between the authenticator and the supplicant. In this case, we can't really do that, so we're going to be basically coming up with a way of stealing credentials so we can authenticate directly with the switch. So let's talk about how we build a rogue device to do that. Basically, the platform that I used was an Intel NUC running Fedora 28, because Fedora 28 has support for MacSEC, which is pretty cool. You'd want to give it three interfaces: a side channel interface so you can control it, an upstream interface that's connected to the switch, a PHY interface that's connected to the supplicant. I threw in a transparent bridge there just because it's useful to have, although it's not really going to be applicable in this case, but more on why we have this when we apply this to other things. But we need a way of diverting traffic to the rogue device. So if you look at these train tracks, I want you to imagine, right? There's like a switch here, and when the switch is in the A position, the train's going to go directly into this train station right here. And when it's in the B position, it's going to bypass the train station entirely. You can do the same style of thing with an Ethernet network. You can buy little mechanical AB Ethernet splitters off of Amazon for like $5 each. They're wonderful. You can take them apart and do things to them. But essentially, you click the A button on one of these things, and traffic will flow into this little thing on the back and out through the A port. You click the B button, and it will switch it so the traffic will be, the two ports that are connected here will be the kind of primary one back here, and the B port. So A, it goes one way, B, it goes the other way. It's a mechanical implementation. It's not affected by the protections that mitigate the bridging that we used earlier. The problem is it doesn't really switch itself. You can buy one that switches itself, but they're like $1,000. So it's easier just to build one. But we need a way of manipulating the push switch. I originally tried using relays, but that led to some pretty crazy impedance issues because I'm not an electrical engineer, which probably explains why if you buy a relay-based one online, they're really expensive. But I think the more easily reproducible option is to use solenoids, which is anyways what I did. Basically, a solenoid is it basically creates linear motion. Essentially, you have a coil that's wrapped around a rod, and when you run electricity through the coil, you either get like a pushing motion if it's a push solenoid, or a pulling motion if it's a pull solenoid. So we essentially use the push solenoids to manipulate the switches and allow us to switch this remotely. And we can control the solenoids with an Arduino. So the final design of a Rogue device is actually going to look like this. It's what we saw before, except now we have a physical AV splitter on each side, so two of them. And the one on the left here is placed between the switch and our upstream interface. And the one on the right here is placed between the phi interface and the supplicant. And what's in the A position, the splitters are bypassing the Rogue device entirely. We set up a LAN tap, a passive tap, which essentially has a one-directional, traffic can flow out of it, but not in. If you look up a throwing star LAN tap, you'll see exactly what I'm talking about. But we place that here when it's in bypass mode, so we can still sniff traffic. And we just that gives us the ability to listen to traffic from the Rogue device. So if we put the switches in, if we run the command to put the switches in the B position, now traffic is routed directly to the device, which puts our device directly between the supplicant and the switch. So you can go back and forth like that. So, with this device, how do we implement the attack? But what we do is we first, once we start out in bypass mode, obviously. But when we want to perform the attack, we bring down the upstream interface, the bridge interface, because we're not really using it, and leave the phi interface up, and we start host APD or listening on the phi interface. And we put these mechanical switches both in mode B. So what that's going to do is that it's going to connect the switch, the authenticator, to this network interface, which is not currently up. So from the switch's perspective, nothing's connected to it. And from the and the other one is going to be basically from the supplicant's perspective. The supplicant is going to be connected to this phi interface, which is running this authentication server. And then we essentially force the supplicant to authenticate. We tell it to re-authenticate by sending it. Well, the way I actually did it was I sent a equal start frame to host APD, which then sends the request identity frame to the supplicant. But that forces authentication. And at that point, it proceeds very much like the attack against weak EAP methods that we just talked about. It authenticates with you, you crack the hashes, and you're done. Then at that point, you can just authenticate with the network directly. You can do this late at night when no one's in the office. People probably won't notice. So to do that, we leave these splitters in the B position. You leave the bridge down. You bring down the phi interface. You bring up the upstream interface with a static IP address that matches the one used by the supplicant. Spoof the supplicant's MAC address, then use the correct credentials to authenticate directly with the switch, and then you're on the network. So just to demonstrate this really fast, same step as before. Although you see here we have this is our little Frankenstein device. You can do this in a much smaller package, but just if you're building something for the first time, it's useful to have large parts to work with, and also for demonstrative purposes, it's easier. We have our 4 solenoids there that are manipulating the splitters, which we've taken apart and integrated them into our little board there. Well, it's not really little, but and it's controlled by this Arduino down there. But same deal. And we're going to run this command, and it's going to implement the Rogue Gateway attack. And you can see these things lighting up, and you can see the solenoids kind of kicking in. And they're flipping those switches so that our supplicant device is connected directly to the switch. Supplicant device is connected directly to our Rogue device. And you see there we're able to capture the hashes. and you can just use those to authenticate. So, yep, that's the attack. Get into we still have some time, so I'm going to do a quick detour, some other stuff that kind of worked on in conjunction with this. We're going to talk quickly about Mac filtering and Mac application authentication bypass. So fun fact, not all devices support 802.1x, and that's surprising, right? But not all devices support 802.1x. And when this happens, in a lot of cases, organizations need to be able to deploy these devices anyways. So a lot of historically, a lot of multifunction printers, IP cameras, peripheral devices like that, they don't have the same kind of 802.1x support that you'd see with things that can be more centrally managed. So when this happens, you don't always have the option to just not deploy this device. You still need to hook it up to the network somehow. So when this happens, you have to create what's known as a port security exception. Essentially port security exception, you're changing your typical port security policies. What this usually means is that you're disabling 802.1x on the port used by this device, and usually replacing it with MAC filtering or some other weak form of access control. And historically, these have been very prevalent due to widespread lack of 802.1x support by these devices, as we talked about. It's also presented historically. It's kind of been viewed as pretty low-hanging fruit by attackers because it's much easier to try to actually to just find a device that has been given a port security exception and spoof a MAC address than to actually have to bypass 802.1x using a bridge or hub. It's much easier, it's much faster, it's much So that's kind of one of the first things you'd look for, rather than actually trying to perform an actual bypass. The thing is, though, port security exceptions are slowly dying. Slowly, I mean, we're not there yet, but it's slow. They are slowly dying. The reason for this is that 802.1x support by peripheral device manufacturers has increased dramatically. Legacy hardware is currently being phased out and replaced by devices that actually do support 802.1x. If you go online and look at like Newegg or just any site that sells enterprise like printers, for example, if you go and look at the different models available, pretty much every major manufacturer out there has at least one brand that supports 802.1x and falls within a price range that could be within the purchasing power of even a lot of small businesses, let alone like an enterprise organization. So what this means is that as the old legacy hardware breaks, it's probably going to get replaced or will be replaced over time with these 802.1x capable models. Which sounds like a good thing because it is making these port security exceptions less prevalent, and really it's really becoming not quite the low-hanging fruit that it used to be, and this is only kind of getting better. Except that improved adoption of 802.1x did not necessarily imply strong port security peripheral devices for a couple of reasons. The first reason, and I can't really fault them for this, but 802.1x 2010 support, it's not really a reality yet for peripheral devices. It's only just starting to take off with everything else. Like the top maybe 2, 3, 4, 5 biggest manufacturers of enterprise networking hardware have MacSEC capable models, but they're all they're all toward the higher end of what you can purchase. Even 802, and also it's complicated to implement. So essentially, 802.1x 2010, it's only just starting to take off in general, and it's something that in terms of peripheral devices, they're not even close. So they're all using, essentially that means they're all using 802.1x 2004. And as we saw, you can bypass that pretty easily using bridges, injections, et cetera. But suppose you don't want to do that. Well, the other interesting thing is that, it kind of, if you think about it, you can expect adoption for secure EAP methods to be significantly lower on peripheral devices than for centrally manageable devices such as domain joined devices. And the reason for that is that adoption of secure EAP methods is already pretty low across the board. And adoption of secure EAP methods can be expected to be even lower for peripheral devices that you can manage from a centralized location. So what this means is that you do have the option of using the rogue gateway attack against 802.1x 2004 if you want to leverage it against these devices. It would play out much in the same way that the attack that we just saw, but instead of you having the switches, you actually could just, if you're using the rogue gateway attack against 802.1x 2004, you don't need the added hardware capabilities. You can just connect the authenticator and the supplicant to your upstream and FI interfaces respectively, and then use that bridge-based approach that we talked about to kind of sit there silently in the middle looking at traffic. And then when you want to perform the rogue gateway attack and actually steal credentials, as before, you bring down the upstream interface, you bring down the bridge, and start a host APD listening on the PHY interface. That will get the supplicant will then authenticate with you, and you'll be able to capture credentials that way, or hashes that you can crack to get credentials. So that'll help you out in cases where these peripheral devices are using EPP or EPTLS, something like that, where you actually have to use a man-in-the-middle attack to get hashes. But actually, interestingly enough, a lot of peripheral devices use EAP-MD5. And the reason for this is, so EAP-MD5, it's a much older, much older EAP method. It's not really that secure, but the thing is, it's very easy to set up and configure, and still better than MAC filtering. So if you need to set up 802.1x on your printer in a pinch, you can pretty much just use EAP-MD5, and you know it's probably going to work, and you're not going to have to fight with it too much. And you can still say that, yes, technically we're deploying 802.1x on everything. We have EAP-MD5 running on all the printers, but who cares, right? So the way EAP-MD5 works, it's going to start out with an EAP request identity frame coming from the authentication server. It's asking the supplicant to provide its username. The supplicant's then going to respond with an EAP response identity, where it's going to provide that username. The authentication server is then going to do something interesting. It's going to basically generate a random string of characters, and it's going to send these off to the send this random string of characters to the supplicant as an EAP response. EAP challenge request. And it's going to send that to the supplicant. The supplicant's going to receive this random string of characters, concatenate it with its username and password to make one long string that's then going to put through the MD5 hash function. The output of the MD5 hash function is then going to get sent off to the authentication server as an EAP response, challenge response. And the authentication server is then going to do the exact same thing. It's going to take the supplicant's password, username, and also the challenge string that generated earlier, and put it through the MD5 hash function itself. And if the output of the hash function is equivalent to the challenge response received from the supplicant, then the authentication server is going to issue an authentication success, and the supplicant's going to be able to connect to the network. Otherwise, it fails and it can't. So the problem with this was once again, this was Brad Antoniewicz and Josh Wright who pointed this out back in 2008, is this entire process is happening over plain text, which is really bad, because if you can sniff this process, you can capture the username, the challenge, and the challenge response, then use a dictionary attack where you successfully try passwords to get those all to line up. And then you can use that to obtain a password using the captured data. Actually, that you don't necessarily have to use a dictionary attack anymore. In 2012, Fanbao Liu and Tao Zi, they figured out that you could actually use a length recovery attack to speed this along even more. So with that in mind, if we leverage what we know about how to attack EAP-MD5 and EAP 2004 and kind of combine them, here's how we would essentially be able to go from this, or from this, should I say, to being able to passively sniff credentials. And let me kind of go back to the slide we're at. You first set up the bridge. You use the bridge-based approach to place a rogue device between the supplicant and authenticator, and then at this point you could just start sniffing traffic. You then wait for the supplicant to authenticate, and then sniff the EAP-MD5 challenge and the EAP-MD5 response, as well as the username when this happens. You then crack the credentials and connect to the network, as we talked about before. The major drawback to this approach is that we have to wait for the supplicant to re-authenticate with the switch. And actually, this is not going to happen unless the supplicant is unplugged realistically. Disabling a virtual network interface usually is not enough to make this happen. We could use mechanical splitters, as we did earlier, to kind of disconnect it and then reconnect it remotely. But the less overhead, the better. So the alternative is to actually use something that I've dubbed the forced re-authentication attack, in which we know how we talked about earlier. The first two steps of the EAP authentication process are as follows. The supplicant's going to send the authenticator an equal start frame, and then the authenticator is going to respond to that with an EAP request identity frame. We talked about how that's optional. And the fact that the first step is optional has security implications, right? Presumably the reason why it's optional is that the authenticator needs a way of getting the authenticator to re-authenticate. The problem is the supplicant has no way of verifying if the incoming EAP request identity frame has been sent in response to an equal start frame. So what this means is that we can force re-authentication by sending an equal start frame to the authenticator as if it came from the supplicant. using MacSEC spoofing. And the result is the authenticator will send an EAP request identity frame to the actual supplicant, kickstarting the re-authentication process. And when this happens, both the authenticator and supplicant believe that the other party has initiated the re-authentication attempt. So it's kind of blind there. And I'll be done in like 2 minutes or so. So just to kind of demonstrate this, here's this thing in action. We're just spamming equal start frames using Scapy, and it's forcing re-authentication. So our revised approach to attacking EAP MD5 in this instance introduced the rogue device into the network between the authenticator and the supplicant, start the transparent bridge and passively snip traffic. Then you force the re-authentication by sending the spoofed equal start frame to the authenticator that forces re-authentication, and then we capture and crack the EAP challenge and EAP MD5 response, and that gives us credentials. It's a very fast attack when this happens. Like you just run it, and we've already got those hazards that we can then crack. All right. Proposed mitigation, I don't actually know, and there's probably might be a way around this, but the first thing that comes to mind is to introduce a safety bit into the EAP requested identity frame. I guess you can read the blog post if you want to know more about that. But just some closing thoughts. So just to go over what we've, the main contributions that we've gone over today. The first is the rogue gateway attack, which can be used to bypass 802.1x 2010 in cases where weak EAP methods are used, and does that by attacking the authentication process itself rather than dealing with MacSEC. We've introduced, updated and improved existing we've basically updated and improved the existing 802.1x 2004 bypass techniques and packaged them in a really easy to use and install tool called Silent Bridge. And also we've introduced the EAP MD5 forced re-authentication attack, which, it's kind of simple, but it makes that, the process of attacking EAP MD5 a lot easier, a lot faster. Some key takeaways. Port security is still a very positive thing. Do not stop using it just because of any of this stuff that I'm talking about today. But it's not a substitute for a layered approach to network security by any means. Deploying 802.1x doesn't absolve anyone from patch management responsibilities, but I'm probably stating the obvious here. The other key takeaways, the benefits provided by 802.1x can be undermined due to, essentially the benefits provided by 802.1x 2010 can be undermined in a lot of cases due to the continued use of EAP as an authentication mechanism. And not only, actually, it's interesting, I don't know if you guys followed any of the research that was released at DEF CON this year, but there was some EAP relay attacks that were released by a couple of guys from SensePost that kind of further make this, actually probably lend itself nicely to this, although I haven't looked into it yet. But yeah, you're still dealing with EAP as the authentication mechanism, and so you can still attack it in the same ways you traditionally attack EAP. Also, improved 802.1x support by peripheral devices is largely undermined by lack of support for 802.1x 2010 and low adoption support rates for strong EAP methods. If you want more in-depth information than what we saw, there's a white paper and blog that you can see at that URL there. And also, if you want to play around with this stuff, there's a tool on GitHub, and I've got the URL for that there. Thank you.